What if I told you that the universe is expanding faster than the speed of light, and yet we can't see most of it? That's right, 95% of the cosmos is made up of dark matter and dark energy, invisible forces that scientists are still struggling to understand. This is just one of the countless mysteries waiting to be unraveled in the vast expanse of space. Welcome to a journey through the cosmos, where we'll uncover 30 hidden facts about our universe that will leave you in awe. From black holes that sing to planets where it rains glass, the universe is far stranger and more fascinating than we could ever imagine. These aren't just random tidbits, they're mind-bending revelations that challenge everything we think we know about reality. So, why should you care? Because the universe isn't just out there, it's a part of us. Every atom in your body was forged in the heart of a star, and the same forces that shaped galaxies are at work in your everyday life. By the end of this video, you'll see the cosmos in a whole new light, and you might just find yourself asking questions you've never thought to ask before. Are you ready to explore the secrets of the universe? From the coldest place in existence to the possibility that we're living in a hologram, this is a journey you won't want to miss. So sit back, open your mind, and let's dive into the wonders of space together. The cosmos is calling, will you answer? Now, let's dive into the first hidden fact about our universe, one that might just change the way you think about everything. The universe isn't just expanding, it's doing so faster than we ever imagined. This discovery, made in the late 1990s, completely upended our understanding of the cosmos. Scientists observed distant supernovae and found that the light from these exploding stars was dimmer than expected, suggesting that the universe's expansion is accelerating. But what's causing this acceleration? Enter dark energy, a mysterious force that makes up about 68% of the universe. Unlike gravity, which pulls things together, dark energy seems to push everything apart, acting like an invisible pressure that's stretching the fabric of space itself. This revelation was groundbreaking because it challenged one of the most fundamental ideas in physics, that the universe's expansion should slow down over time due to gravity. Instead, dark energy is driving the cosmos to expand faster and faster, raising questions about the ultimate fate of the universe. Will it keep expanding forever, tearing galaxies apart until everything is cold and dark? Or could dark energy change over time, leading to a different outcome? What's even more fascinating is that we still don't fully understand what dark energy is. It doesn't interact with light or matter in any way we can detect, making it one of the greatest mysteries in modern science. Some theories suggest it's a property of space itself, while others propose entirely new forces or dimensions. Whatever the answer, this discovery reminds us that the universe is far more complex and unpredictable than we once thought. So, as we ponder the accelerating expansion of the cosmos, we're left with more questions than answers. But that's the beauty of science, it's a journey of discovery, and every mystery we uncover only deepens our sense of wonder. And speaking of mysteries, let's move on to the next hidden fact, where we'll explore just how vast the universe truly is. Now, shifting our gaze to the sheer scale of the cosmos, let's explore a fact that truly puts the universe's immensity into perspective. Did you know there are more stars in the observable universe than grains of sand on all the beaches and deserts of Earth? It's a staggering comparison that highlights just how vast and mysterious space really is. To give you an idea, scientists estimate there are around 100 billion galaxies in the observable universe, each containing hundreds of billions of stars. That adds up to roughly 1 septillion stars. That's a 1 followed by 24 zeros. Now compare that to the grains of sand on Earth. If you were to count every grain on every beach, desert, and sand dune, you'd end up with a number in the trillions, still enormous, but nowhere near the number of stars out there. This mind-blowing fact isn't just about big numbers, it's a reminder of how much we have yet to discover. With so many stars, each potentially hosting its own planets, the possibilities for undiscovered worlds are endless. Imagine the diversity of planets that could exist, some with oceans of liquid water, others with skies filled with multiple suns, and perhaps even worlds teeming with life we can't yet imagine. What's even more humbling is that the observable universe, the part we can see, is just a tiny fraction of the entire cosmos. Beyond what our telescopes can detect, there could be countless more stars, galaxies, and mysteries waiting to be uncovered. This fact not only underscores the vastness of space, but also invites us to dream about what lies beyond our current understanding. So, the next time you're standing on a beach, take a moment to look at the sand beneath your feet. Then look up at the night sky and remember every grain of sand represents just a fraction of the stars above, each one a beacon of light in the endless expanse of the universe. And as we continue our journey through these hidden facts, we'll uncover even more wonders that remind us just how small yet connected we are in this grand cosmic tapestry. Now, turning to one of the most fascinating and eerie phenomena in the cosmos, let's dive into the mysterious world of black holes and their ability to sing. Yes, you heard that right. Black holes, those enigmatic regions of space where gravity is so strong that not even light can escape, can produce sound. But how does something so silent and dark create something as vibrant as music? The answer lies in the gas and dust swirling around black holes. As these materials spiral inward, they form what's called an accretion disk, a superheated, chaotic whirlpool of matter. The intense gravitational forces and friction within this disk generate pressure waves which ripple through the surrounding gas. These waves, when translated into sound, create what scientists describe as eerie songs. In 2003, astronomers detected these sound waves emanating from a supermassive black hole at the center of the Perseus galaxy cluster. Using data from NASA's Chandra X-ray Observatory, they found that the pressure waves caused ripples in the hot gas surrounding the black hole. When these ripples were converted into sound, they produced a deep, resonant tone, a note that's about 57 octaves below middle C on a piano. To put that in perspective, it's a sound so low that it's far beyond the range of human hearing. But why does this matter? Beyond the sheer cool factor of a singing black hole, this phenomenon helps scientists understand the behavior of black holes and their impact on their surroundings. The sound waves carry energy which can heat up the surrounding gas and influence the formation of stars and galaxies. This means black holes aren't just cosmic vacuum cleaners, they're active players in shaping the universe. What's even more intriguing is that these songs can vary. Different black holes, depending on their size and the amount of material they're consuming, can produce different tones. Some might hum softly, while others could roar like a cosmic bass. It's a symphony of the universe, one that's been playing for billions of years, even if we've only just begun to listen. So, the next time you think of black holes as silent, lifeless voids, remember, they're anything but. They're cosmic musicians creating soundscapes that echo through the fabric of space and time. And as we continue to explore these mysterious objects, who knows what other secrets they might reveal? For now, let's marvel at the fact that even in the darkest corners of the universe, there's a song waiting to be heard. Now, shifting our focus from the cosmic symphony of black holes to the icy extremes of temperature, let's explore a surprising fact. The coldest place in the universe isn't in the depths of space, it's right here on Earth. In laboratories around the world, scientists have achieved temperatures so low that they come within a fraction of a degree of absolute zero, the theoretical point where all molecular motion stops. This staggering achievement not only pushes the boundaries of human ingenuity, but also opens up new frontiers in our understanding of physics. Absolute zero, which is minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit, is the coldest temperature possible in the universe. At this point, atoms and molecules would theoretically cease all movement. While reaching absolute zero is impossible due to the laws of quantum mechanics, scientists have come incredibly close. In labs like NAS, a cold atom laboratory, and facilities using Bose-Einstein condensates, researchers have cooled matter to just a billionth of a degree above absolute zero. To put that into perspective, the vacuum of space, which is already incredibly cold at around -270 degrees Celsius, feels warm compared to these ultra-cold experiments. But why go to such extremes? The pursuit of ultra-cold temperatures isn't just about breaking records, it's about unlocking the secrets of the universe. At these frigid temperatures, matter behaves in bizarre and fascinating ways. For example, atoms can form a state of matter called a Bose-Einstein condensate, where they lose their individual identities and act as a single quantum entity. This allows scientists to study quantum mechanics in ways that were previously impossible, shedding light on phenomena like superconductivity and superfluidity. These discoveries could revolutionize technology, leading to advancements in quantum computing, energy efficiency, and even space exploration. The implications of this research extend far beyond the lab. By studying matter at these extreme temperatures, scientists can simulate conditions that existed just moments after the Big Bang, offering clues about the origins of the universe. It also helps us understand the behavior of exotic materials and particles, paving the way for innovations that could transform our daily lives. From more efficient power grids to faster, more powerful computers, the applications of ultra-cold physics are as vast as they are exciting. So, while the universe is filled with extremes from the scorching heat of stars to the icy void of space, it's remarkable to think that some of the coldest temperatures ever recorded exist right here on our planet. This achievement is a testament to human curiosity and our relentless drive to explore the unknown. And as we continue to push the boundaries of what's possible, who knows what other cosmic secrets we might uncover. For now, let's marvel at the fact that even in the coldest corners of science, there's a universe of discovery waiting to be explored. Now, turning our gaze from the icy extremes of Earth to the vast emptiness of space, let's explore one of the most puzzling features of the cosmos, the Boötes Void. Imagine a region of space so empty, so devoid of galaxies, stars, and even dust, that it feels like a cosmic desert stretching across billions of light years. This is the Boötes Void, one of the largest known voids in the universe, and it challenges everything we thought we knew about the structure of the cosmos. The Boötes Void, also known as the Great Void, spans an astonishing 330 million light-years across. To put that into perspective, if you place the Milky Way at one end of the void, it would take light traveling at 300,000 kilometers per second, over 300 million years to reach the other side. And yet, despite its immense size, this void contains only a handful of galaxies, making it one of the emptiest places in the known universe. For comparison, a typical region of space of the same size would contain thousands of galaxies. So, how does something like the Boötes Void form? Cosmic voids like this are thought to be the result of the universe's large-scale structure, which resembles a cosmic web. Picture the universe as a sponge, with galaxies clustered along the filaments of the web and vast empty spaces in between. These voids are the gaps in the sponge, regions where matter is scarce. But the Boötes Void is so unusually large and empty that it defies even this explanation. Some scientists believe it could be the result of smaller voids merging over billions of years, while others speculate that it might hint at unknown forces or phenomena at work in the early universe. The existence of such voids challenges our understanding of how the universe evolved after the Big Bang. According to the standard model of cosmology, matter should be distributed more or less evenly across the universe with only slight variations. But the Boötes Void, with its staggering emptiness, suggests that the distribution of matter might be far more uneven than we thought. This raises questions about the nature of dark energy and dark matter, the mysterious components that make up most of the universe. Could these voids be evidence of something we're missing in our current theories? Despite their emptiness, cosmic voids like the Boötes Void play a crucial role in shaping the universe. They act as cosmic pressure chambers, influencing the movement of galaxies and the growth of large-scale structures. By studying these voids, scientists can learn more about the forces that govern the universe and how it has evolved over billions of years. They also provide a unique laboratory for testing theories about gravity, dark energy, and the ultimate fate of the cosmos. So, while the Boötes Void might seem like a barren, unremarkable stretch of space, it's actually a window into some of the deepest mysteries of the universe. Its existence reminds us that even in the vastness of space, there are still uncharted territories waiting to be explored. And as we continue to study these cosmic voids, who knows what other secrets they might reveal about the universe we call home? Now, shifting our focus from the vast emptiness of cosmic voids to the unimaginable density of neutron stars, let's dive into one of the most extreme objects in the universe. Neutron stars are the remnants of massive stars that have exhausted their fuel and collapsed under their own gravity. What makes them truly extraordinary is their density so extreme that a single sugar cube-sized piece of neutron star material would weigh as much as a mountain here on Earth. To put it another way, if you could scoop up just a teaspoon of this material, it would weigh over 1 billion tons. That's the kind of density we're talking about, mind-bending to say the least. So how do neutron stars form? When a massive star, at least 8 times heavier than our Sun, reaches the end of its life, it explodes in a spectacular supernova. What's left behind is the star's core, which collapses under its own gravity. The pressure becomes so intense that protons and electrons are crushed together, forming neutrons. The result is a neutron star, a city-sized object, typically only about 20 kilometers across, but packing the mass of 1.4 times that of our Sun. It's like taking the entire mass of a star and squeezing it into a space no larger than a small city. But neutron stars aren't just dense, they're also incredibly dynamic. Many of them spin at astonishing speeds, completing hundreds of rotations every second. These rapidly spinning neutron stars, known as pulsars, emit beams of radiation from their magnetic poles. As they spin, these beams sweep across the sky like cosmic lighthouses, and if they happen to point toward Earth, we detect them as regular pulses of light or radio waves. This makes pulsars some of the most precise clocks in the universe, helping scientists test theories of gravity and even detect gravitational waves. Neutron stars also play a crucial role in the cosmos. When two neutron stars collide, they create ripples in space-time called gravitational waves, which scientists can detect here on Earth. These collisions also produce heavy elements like gold and platinum, scattering them across the universe. In fact, much of the gold in your jewelry likely originated from a neutron star collision billions of years ago. So, in a way, neutron stars are cosmic alchemists, transforming ordinary matter into some of the most precious elements in the universe. Despite their small size, neutron stars are powerhouses of physics. They challenge our understanding of matter under extreme conditions, where the rules of quantum mechanics and gravity collide. Studying them helps us explore the limits of what's possible in the universe and sheds light on the fundamental forces that govern everything from the smallest particles to the largest structures in space. So, while neutron stars might seem like distant, exotic objects, they're actually key to unlocking some of the universe's greatest mysteries. And as we continue to study them, who knows what other secrets they might reveal about the cosmos? Now, shifting our gaze from the incredible density of neutron stars to the grand architecture of the universe, let's explore the cosmic web, a vast, intricate network that connects everything in the cosmos. Imagine the universe not as a random scattering of galaxies, but as a carefully woven tapestry with galaxies strung together like beads on invisible threads. This is the cosmic web, the large-scale structure of the universe, and it's one of the most fascinating frameworks in all of science. At its core, the cosmic web is made up of galaxies, clusters of galaxies, and the mysterious dark matter that binds them together. These galaxies aren't just floating aimlessly in space, they're connected by long, thin filaments of dark matter, forming a web-like structure that stretches across billions of light years. These filaments act like cosmic highways, guiding the flow of matter and energy throughout the universe. Where these filaments intersect, you'll find dense clusters of galaxies, while the spaces between them are vast, empty voids. But how did this cosmic web come to be? It all goes back to the early universe, just moments after the Big Bang. Tiny fluctuations in the density of matter, some regions slightly denser, others slightly less dense, set the stage for the web's formation. Over billions of years, gravity amplified these differences, pulling matter into the denser regions and leaving the less dense areas empty. The result is the intricate network we see today, with galaxies and clusters strung along the filaments like pearls on a necklace. Dark matter plays a crucial role in this structure. Though invisible and undetectable by conventional means, dark matter makes up about 85% of the universe's total matter. Its gravitational pull is what holds the cosmic web together, shaping the distribution of galaxies and influencing how they move and interact. Without dark matter, the universe would look very different, far less organized and far more chaotic. The cosmic web isn't just a static structure, it's dynamic and ever-changing. Galaxies move along the filaments, drawn toward the densest clusters by gravity. Over time, these clusters grow larger as they pull in more galaxies, while the voids between them expand. This constant motion and evolution give the cosmic web a sense of life, as if the universe itself is breathing and growing. Understanding the cosmic web helps us answer some of the biggest questions in cosmology. It reveals how matter is distributed across the universe, how galaxies form and evolve, and even how the universe itself is expanding. By studying this vast network, scientists can piece together the story of the cosmos, from its earliest moments to its ultimate fate. So, the next time you look up at the night sky, remember that the stars and galaxies you see are part of something much larger, a cosmic web that connects everything in the universe. It's a reminder of how intricately woven the cosmos truly is, and how much we still have to learn about its mysteries. And as we continue to explore this grand structure, who knows what other secrets it might reveal about the nature of reality itself. Now, as we venture into the realm of relativity, let's uncover one of the most mind-bending truths about our universe. Time itself is not constant. In fact, time passes differently depending on where you are and how fast you're moving. This phenomenon, predicted by Albert Einstein's theory of relativity, reveals that time can slow down or speed up under certain conditions, and it's not just science fiction. It's a reality that shapes our understanding of the cosmos. Imagine you're an astronaut orbiting Earth in the International Space Station. While you're up there, floating hundreds of kilometers above the planet, time for you is actually passing slightly slower than it is for someone standing on Earth's surface. This happens because of two key factors, gravity and speed. The stronger the gravitational pull, the slower time moves, and the faster you travel, the more time slows down relative to someone moving at a slower speed. This means that astronauts, who are both farther from Earth's gravity and moving at incredible speeds, experience time just a tiny bit slower than we do on the ground. Over the course of a 6-month mission, an astronaut might age about 0.007 seconds less than someone on Earth. It's a small difference, but it's real, and it's proof that time is far more flexible than we might think. But the effects of relativity become even more dramatic near massive objects like black holes. If you were to hover near the edge of a black hole, where gravity is unimaginably strong, time would slow down so much that just a few minutes for you could equal years or even centuries for someone far away. This extreme time dilation is a direct result of the intense gravitational pull warping the fabric of spacetime itself. It's a concept that challenges our everyday experience of time as something steady and unchanging, reminding us that the universe operates by rules that are often stranger than fiction. Even here on Earth, relativity plays a role in our daily lives, though the effects are incredibly subtle. For example, GPS satellites, which orbit high above the planet and travel at high speeds, have to account for the fact that their onboard clocks tick slightly faster than clocks on the ground. Without adjusting for this difference, GPS systems would be off by several kilometers, making navigation nearly impossible. It's a practical application of relativity that most of us rely on without even realizing it. So, what does this mean for our understanding of the universe? It shows us that time is not a universal constant, but a dynamic, ever-changing dimension influenced by gravity and motion. It challenges our perception of reality and opens up profound questions about the nature of existence. And as we continue to explore the cosmos, from the depths of black holes to the vastness of interstellar space, the mysteries of time will remain one of the most fascinating frontiers of science. As we ponder the fluidity of time, let's turn our attention to another cosmic wonder, a planet so exotic it's made almost entirely of diamond. But that's a story for the next chapter of our journey through the universe's hidden secrets. Now, shifting our gaze to the glittering wonders of the cosmos, let's explore a planet that sounds like it belongs in a science fiction novel, a world made almost entirely of diamond. This extraordinary discovery, known as 55 Cancri E, is one of the most fascinating and exotic planets ever found. Located about 40 light-years from Earth, this super-Earth orbits so close to its star that its surface is a scorching inferno, with temperatures reaching thousands of degrees Celsius. But what truly sets this planet apart is its composition. Scientists believe it's largely made of carbon, compressed under immense pressure into crystalline structures, essentially forming a planet-sized diamond. So, how does a diamond planet come to exist? The story begins with the star it orbits. 55 Cancri E's parent star is rich in carbon, a key ingredient for diamond formation. When the planet formed, it likely accumulated vast amounts of carbon from its surroundings. Under the extreme pressures and temperatures found deep within the planet, this carbon was compressed into diamond. Imagine a world where the ground beneath your feet, if you could stand on it, would be a glittering expanse of solid diamond. It's a breathtaking reminder of the incredible diversity of celestial bodies in our universe. But 55 Cancri E isn't just a cosmic curiosity. It also offers valuable insights into planetary formation and the variety of worlds that exist beyond our solar system. Its discovery challenges our assumptions about what planets can be made of and how they evolve. While Earth is rich in oxygen and silicon, planets like 55 Cancri E remind us that the universe is full of surprises, with environments and compositions that defy our imagination. This diamond planet is a testament to the endless possibilities that await us as we continue to explore the cosmos. As we marvel at this glittering world, let's prepare to uncover another cosmic marvel, a star that's almost as old as the universe itself. But that's a story for the next chapter of our journey through the universe's hidden secrets. Now, turning to the heart of our solar system, let's dive into the incredible journey of energy within the Sun. At its core, the Sun is a powerhouse of nuclear fusion, where hydrogen atoms collide under immense pressure and temperature, fusing to form helium. This process releases an enormous amount of energy in the form of photons or light particles. But here's the astonishing part. The energy created in the Sun's core doesn't just zip straight to the surface. Instead, it embarks on a slow, winding journey that can take tens of thousands of years. Imagine a photon born in the Sun's core. It doesn't travel in a straight line. Instead, it bounces around, colliding with other particles in the dense plasma. This process, known as the radiative zone, is like a cosmic game of pinball where the photon is constantly absorbed and re-emitted by atoms. Over time, it gradually makes its way outward, but at a snail's pace. By the time it reaches the sun's surface, thousands of years may have passed. Only then does it finally break free, racing through space at the speed of light to reach Earth in just 8 minutes. This slow journey highlights the incredible density and complexity of the sun's interior. It also underscores the delicate balance that keeps our star shining. Without this intricate process, the energy needed to sustain life on Earth would never reach us. The sun's core is a testament to the power of nuclear fusion and the remarkable physics that govern our universe. As we reflect on this cosmic journey, let's prepare to explore another fascinating phenomenon: the moon's gradual drift away from Earth. But that's a story for the next chapter of our cosmic adventure. Now, shifting our gaze from the sun to our closest celestial neighbor, let's uncover a subtle yet profound change happening right above us. The moon, Earth's faithful companion, is slowly but steadily drifting away from us. Each year, the moon moves approximately 3.8 centimeters farther from Earth. While that might not sound like much over millions of years, this tiny shift adds up to a significant change. This gradual movement is driven by tidal forces, a fascinating interplay between Earth and the moon. As the moon's gravity pulls on Earth, it creates bulges in our planet's oceans known as tides. These tidal bulges, in turn, exert a gravitational pull on the moon, giving it a slight nudge in its orbit. This energy transfer causes the moon to spiral outward, increasing its distance from Earth over time. It's a cosmic dance of gravity and motion, one that has been unfolding for billions of years. But what does this mean for Earth in the long run? As the moon drifts farther away, its gravitational influence on our planet will weaken. This could lead to slower ocean tides and even changes in Earth's rotation. Over billions of years, days on Earth could grow longer, and the delicate balance of our planet's climate and ecosystems could be affected. While these changes are far in the future, they remind us of the intricate connections that bind Earth and the moon together. As we ponder the moon's slow retreat, let's turn our attention to another cosmic marvel: a cloud in space filled with billions of liters of alcohol. But that's a story for the next chapter of our journey through the universe. Now, let's venture into a truly intoxicating corner of the cosmos. Deep within the constellation of Sagittarius, there's a massive molecular cloud known as Sagittarius B2, and it's not your ordinary cloud. This cosmic giant contains billions of liters of alcohol, including ethanol and methanol, floating freely in space. Yes, you heard that right, alcohol, the kind you might find in a drink, exists in staggering quantities out there among the stars. But how does a cloud like this form? Molecular clouds like Sagittarius B2 are vast regions of gas and dust, often spanning hundreds of light years. They are the birthplaces of stars and planets, where gravity pulls together particles over millions of years, creating dense pockets that eventually ignite into stars. Within these clouds, complex chemical reactions occur, producing a variety of molecules, including organic compounds like alcohol. The presence of alcohol in Sagittarius B2 is a testament to the rich chemistry that takes place in these stellar nurseries. What's even more fascinating is the role these clouds play in the universe. As stars and planets form within them, they carry with them the building blocks of life, including water, carbon, and yes, even alcohol. These molecules become part of the raw materials that shape new worlds, potentially seeding them with the ingredients necessary for life. So, while Sagittarius B2 might sound like a cosmic bar, it's actually a crucial part of the universe's life cycle, where the seeds of stars, planets, and perhaps even life itself are sown. As we marvel at this alcoholic cloud, let's not forget that it's just one of countless wonders waiting to be discovered in the vast expanse of space. And speaking of wonders, our next stop takes us to the very echoes of the Big Bang itself. A faint hum that permeates the universe, but that's a story for the next chapter. Now, shifting our gaze to the very fabric of the cosmos, we encounter a phenomenon that whispers the secrets of the universe's birth. This is the cosmic microwave background radiation, often referred to as the universe's background hum. Imagine it as the faint echo of the Big Bang, a relic from the moment the universe burst into existence over 13.8 billion years ago. This radiation is everywhere, filling every corner of space, and it's one of the most profound pieces of evidence we have for understanding how everything began. So, what exactly is this cosmic hum? Picture the universe in its infancy, just a few 100,000 years after the Big Bang. At that time, the cosmos was a seething, dense soup of particles and energy. As the universe expanded and cooled, light was finally able to travel freely, creating a glow that has been stretched and cooled over billions of years into the microwave radiation we detect today. This glow is like a snapshot of the universe at its earliest stages, a cosmic baby photo that reveals the conditions of the universe when it was just a fraction of its current size. The discovery of this background radiation was a monumental moment in cosmology. In the 1960s, two scientists, Arno Penzias and Robert Wilson, accidentally stumbled upon this faint signal while working with a radio telescope. At first, they thought it was interference, but soon realized they had found something far more significant: the afterglow of the Big Bang itself. This discovery provided crucial evidence for the Big Bang theory and earned them the Nobel Prize in Physics. But the cosmic microwave background isn't just a historical artifact. It's a treasure trove of information for scientists. By studying the tiny fluctuations in this radiation, cosmologists can map the early universe's structure, revealing the seeds of galaxies and galaxy clusters that would form billions of years later. These fluctuations are like cosmic fingerprints, offering clues about the universe's composition, its rate of expansion, and even the nature of dark energy and dark matter. In essence, the cosmic microwave background is a time capsule, a window into the universe's earliest moments. It's a reminder that the cosmos is not just a vast, empty space, but a dynamic, evolving entity with a rich history. And as we continue to study this ancient hum, we uncover more about the origins of everything we see, and even what we cannot see. With this hum still resonating in our minds, let's turn our attention to another cosmic mystery: stars that seem to defy the very age of the universe itself. But that's a story for the next chapter. Now, as we venture deeper into the cosmos, we encounter a paradox that challenges our very understanding of time and existence. Imagine a star so ancient that it seems to predate the universe itself. This is the mystery of Methuselah, a star officially known as HD 140283, which appears to be older than the universe's estimated age of 13.8 billion years. How can a star exist before the universe? This cosmic conundrum has sparked intense debate among scientists and continues to baffle even the most seasoned astronomers. Methuselah, located in the constellation Libra, is one of the oldest known stars in the Milky Way. Through careful analysis of its composition and brightness, astronomers initially estimated its age to be around 14.5 billion years, nearly a billion years older than the universe itself. This finding, of course, is impossible according to our current understanding of cosmology. So, what's really going on here? One explanation lies in the uncertainties of stellar age measurements. Determining the age of a star is no simple task. It involves analyzing its chemical composition, brightness, and distance, all of which can introduce errors. Methuselah's age estimate was based on its low metal content, a characteristic of ancient stars that formed before heavier elements were abundant in the universe. However, recent studies suggest that the star's age might have been overestimated due to factors like its unusual chemical makeup or the way it interacts with its environment. Revised calculations now place Methuselah's age closer to 13.7 billion years, just shy of the universe's age, though the debate is far from settled. Another intriguing possibility is that our understanding of the universe's age might need refinement. While the current estimate of 13.8 billion years is based on the cosmic microwave background and the rate of universal expansion, there's always room for new discoveries to shift this number. Could Methuselah be a clue that the universe is slightly older than we think, or does it point to gaps in our knowledge about how stars form and evolve? This paradox also highlights the complexity of cosmic timelines. Stars like Methuselah are relics from the universe's earliest days, offering glimpses into a time when galaxies were just beginning to take shape. By studying these ancient stars, scientists hope to unravel the mysteries of the universe's infancy and refine our understanding of its origins. As we ponder the enigma of Methuselah, we're reminded that the cosmos is full of surprises, constantly challenging our assumptions and pushing the boundaries of what we know. And with that, let's turn our attention to another celestial wonder, a planet where the weather is as extreme as it gets, but that's a story for the next chapter. Now, shifting our gaze to a world that defies imagination, we arrive at HD 189733b, a planet where the weather is as bizarre as it is deadly. This distant world, located 63 light-years away in the constellation Vulpecula, is a gas giant with a twist. Its atmosphere is filled with silicate particles, which condense into glass and rain sideways at speeds of up to 5,000 miles per hour. Yes, you heard that right. On this planet, it literally rains glass. But how does such a phenomenon occur? HD 189733b orbits extremely close to its host star, completing a full orbit in just 2.2 Earth days. This proximity subjects the planet to scorching temperatures, reaching up to 1,700 degrees Fahrenheit on its day side. The intense heat vaporizes silicate minerals in the atmosphere, creating tiny particles of glass. These particles are then swept up by supersonic winds, which can reach speeds 7 times the speed of sound, creating a relentless, sideways glass rain. The planet's atmosphere is also a deep, vivid blue, reminiscent of Earth's oceans. But don't let the color fool you. This is no serene paradise. The blue hue comes from the scattering of light by the silicate particles, giving the planet its striking appearance. However, beneath this beautiful facade lies a chaotic and hostile environment, where the weather is as extreme as it gets. What makes HD 189733b particularly fascinating is that it provides a glimpse into the diversity of planetary atmospheres. While Earth's weather systems are driven by water and air, this distant world showcases how different materials and conditions can create entirely unique meteorological phenomena. Studying planets like this helps scientists understand the vast range of possibilities in the universe, from scorching gas giants to icy, barren worlds. As we marvel at the strange and violent beauty of HD 189733b, we're reminded once again that the universe is a place of endless wonder and surprise. And with that, let's turn our attention to another cosmic mystery, a theory that suggests our entire universe might be nothing more than a hologram, but that's a story for the next chapter. Now, stepping into the realm of the truly mind-bending, we arrive at a theory that challenges everything we think we know about reality, the holographic principle. This idea suggests that our universe, with all its vastness and complexity, might actually be a two-dimensional projection like a cosmic hologram. Imagine the entire cosmos as a kind of giant movie screen where everything we see, touch, and experience is just a projection from a flat, two-dimensional surface. It sounds like science fiction, but some of the brightest minds in physics are taking this idea seriously. The holographic principle emerged from the study of black holes and the strange behavior of information at their boundaries. Scientists discovered that all the information about matter falling into a black hole could be encoded on its surface or event horizon in 2 dimensions. This led to the radical idea that perhaps the entire universe operates in a similar way, that the 3-dimensional reality we perceive is just a projection of information stored on a 2-dimensional surface at the edge of the cosmos. One of the key pieces of evidence supporting this theory comes from the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Researchers have found patterns in this radiation that seem to align with the predictions of the holographic principle. These patterns suggest that the universe might indeed be encoded with information in a way that resembles a hologram. If the holographic principle is true, it would have profound implications for our understanding of space, time, and reality itself. It could mean that the universe is fundamentally simpler than we thought, with all its complexity emerging from a simpler, two-dimensional framework. It might also help resolve some of the biggest puzzles in physics, such as the nature of gravity and the unification of quantum mechanics with general relativity. But what does this mean for us? If the universe is a hologram, does that make our lives any less real? Not necessarily. Even if reality is a projection, the experiences we have, the emotions we feel, and the connections we share are still very much real to us. The holographic principle doesn't diminish the wonder of existence. It simply adds another layer of mystery to the cosmos. As we ponder this extraordinary idea, we're reminded once again that the universe is far stranger and more fascinating than we can imagine. And with that, let's turn our attention to another cosmic enigma, a galaxy made almost entirely of dark matter. But that's a story for the next chapter. Now, shifting our gaze to the mysterious depths of the cosmos, we encounter a galaxy that defies conventional understanding: Dragonfly 44. This enigmatic galaxy, located in the Coma cluster, is composed almost entirely of dark matter, a substance that neither emits nor reflects light, making it invisible to traditional telescopes. Despite its massive size, comparable to our Milky Way, Dragonfly 44 emits only a faint glow, revealing just a fraction of the stars we'd expect in a galaxy of its scale. This peculiarity has left scientists both baffled and fascinated. Dark matter, which makes up about 85% of the universe's total mass, has long been a puzzle for astronomers. While its presence is inferred through its gravitational effects on visible matter, its true nature remains one of the greatest mysteries in science. Dragonfly 44, with its staggering 99.9% dark matter composition, challenges our understanding of how galaxies form and evolve. Unlike typical galaxies where stars and gas dominate, Dragonfly 44 seems to be held together almost entirely by the gravitational pull of dark matter. The discovery of such galaxies raises profound questions about the universe's composition. How do galaxies like Dragonfly 44 form? Why do they contain so few stars compared to their dark matter content? And what role does dark matter play in shaping the cosmos on such a grand scale? These questions push scientists to rethink existing theories about galaxy formation and the interplay between dark matter and visible matter. One leading hypothesis suggests that Dragonfly 44 might be a failed galaxy, one that never accumulated enough gas to form a significant number of stars. Alternatively, it could represent a new class of galaxies where dark matter dominates in ways we're only beginning to understand. Whatever the case, Dragonfly 44 serves as a stark reminder of how much we still have to learn about the universe's hidden architecture. As we continue to explore the cosmos, galaxies like Dragonfly 44 remind us that the universe is full of surprises, waiting to challenge our assumptions and expand our understanding. And with that, we turn our attention to another cosmic marvel, the largest known structure in the universe, a colossal wall of galaxies stretching across billions of light years. But that's a story for the next chapter. Now, as we venture further into the vast expanse of the cosmos, we encounter a structure so immense that it challenges our very perception of scale: the Hercules Corona Borealis Great Wall. This colossal formation, stretching over 10 billion light-years, is the largest known structure in the universe. To put that into perspective, if you were to travel at the speed of light, it would take you 10 billion years to cross from one end to the other. That's more than half the age of the universe itself. The Hercules Corona Borealis Great Wall is not a physical wall in the traditional sense, but rather a vast filament of galaxies, galaxy clusters, and dark matter, all interconnected in a web-like structure. Discovered in 2013, this cosmic behemoth defies the cosmological principle, which suggests that the universe should appear relatively uniform on the largest scales. Instead, the Great Wall reveals a universe filled with irregularities and structures that stretch the limits of our understanding. What makes this discovery so significant is its sheer size. The Great Wall dwarfs other known structures, such as the Sloan Great Wall, which spans a mere 1.4 billion light-years. Its existence raises profound questions about the early universe and the forces that shaped it. How did such a massive structure form? What processes allowed galaxies and dark matter to cluster on such an unimaginable scale? These questions push scientists to refine their models of cosmic evolution and the role of dark energy in the universe's expansion. One theory suggests that the Great Wall formed due to fluctuations in the density of matter shortly after the Big Bang. Over billions of years, gravity amplified these fluctuations, pulling matter together into the vast filaments we observe today. Yet, even this explanation leaves room for debate, as the scale of the Great Wall seems to stretch the boundaries of what our current theories can account for. The discovery of the Hercules Corona Borealis Great Wall not only highlights the universe's grandeur, but also underscores how much we have yet to learn. It serves as a reminder that the cosmos is far more complex and mysterious than we often imagine. As we continue to map the universe, structures like this challenge us to rethink our assumptions and explore new frontiers in our quest to understand the cosmos. And with that, we turn our attention to another cosmic wonder, a star so ancient that it offers a glimpse into the universe's earliest days. But that's a story for the next chapter. Now, shifting our gaze to a star that has witnessed the dawn of time itself, we encounter SMSS J031300, 36,670,839. 3, a celestial relic that stands as one of the oldest known stars in the universe. Discovered in 2014, this ancient star is estimated to be around 13.6 billion years old, making it nearly as old as the universe itself. To put that into perspective, this star formed just a few 100 million years after the Big Bang, during a time when the cosmos was still in its infancy. What makes SMSS J031300, 36,670,839, 3 so extraordinary is its composition. Unlike younger stars, which contain heavier elements like iron and carbon, this ancient star is almost entirely made up of hydrogen and helium, the simplest and lightest elements in existence. This lack of heavier elements, known as metals in astronomical terms, suggests that SMSS J031300, 36,670,839, 3 formed from the primordial gas that filled the early universe before the first generations of stars had time to forge heavier elements through nuclear fusion. The discovery of this star provides a rare window into the universe's earliest days. By studying its composition, scientists can piece together the conditions that existed shortly after the Big Bang and gain insights into the formation of the first stars, often referred to as population 3 stars. These stars, which have never been directly observed, are believed to have been massive and short-lived, exploding as supernova and seeding the universe with the heavier elements that would later form planets, life, and stars like our Sun. One of the most intriguing aspects of SMSS J031300, 36,670,839, 3 is its unusually low iron content. While most stars contain at least some iron, this star has an iron-to-hydrogen ratio that is more than 1,000,000 times lower than that of the Sun. This suggests that it formed from material that had been enriched by just a single supernova, providing a snapshot of the universe's chemical evolution at a very early stage. The existence of such ancient stars challenges our understanding of star formation in the early universe. How did these stars form in an environment so different from today's cosmos? What processes allowed them to survive for billions of years, preserving their pristine composition? These questions drive astronomers to refine their models of the early universe and explore the origins of the first stars and galaxies. As we continue to study stars like SMSS J03 1300, 36,670,839, we uncover clues about the universe's infancy and the forces that shaped its evolution. These ancient stars serve as cosmic time capsules, offering a glimpse into a time when the universe was young, chaotic, and full of potential. And with that, we turn our attention to another cosmic mystery, the missing baryon problem, a puzzle that challenges our understanding of the universe's composition. But more on that in the next chapter. Now, turning to a cosmic mystery that has puzzled scientists for decades, we delve into the universe's missing baryon problem. Baryonic matter, the ordinary stuff that makes up stars, planets, and even us, is thought to account for about 5% of the universe's total mass and energy. Yet, when astronomers tally up all the visible matter in the cosmos, they find that a significant portion of it is unaccounted for. This discrepancy is what scientists call the missing baryon problem. So, where is all this missing matter hiding? The answer lies in the vast, diffuse regions of space between galaxies. While stars and galaxies are easy to spot, much of the universe's baryonic matter exists in the form of hot, thin gas that's incredibly difficult to detect. This gas, known as the warm-hot intergalactic medium, or WIM, is spread out across the cosmic web, the large-scale structure of the universe. The WIM is so faint and diffuse that it doesn't emit enough light for traditional telescopes to observe directly. Instead, scientists rely on indirect methods, such as studying how this gas absorbs light from distant quasars to detect its presence. One leading theory suggests that the missing baryons are tied up in these vast filaments of gas, which connect galaxies like threads in a cosmic tapestry. These filaments are thought to contain a significant portion of the universe's baryonic matter, but their elusive nature makes them a challenge to study. Another possibility is that some of the missing matter exists in the form of faint, low-mass stars or rogue planets that drift through space undetected. However, these objects are difficult to observe, and their contribution to the missing baryon problem remains uncertain. Efforts to solve this mystery are ongoing, with astronomers using advanced telescopes and innovative techniques to map the distribution of baryonic matter across the universe. For example, the Atacama Large Millimeter Array, or ALMA, and the upcoming James Webb Space Telescope are expected to provide new insights into the properties of the WIM and other elusive components of the cosmic web. Additionally, computer simulations of the universe's evolution are helping scientists predict where this missing matter might be hiding and how it could be detected. The missing baryon problem is more than just a cosmic accounting error. It's a fundamental question about the structure and composition of the universe. Solving this puzzle could help us better understand how galaxies form and evolve, as well as the role of baryonic matter in shaping the cosmos. As we continue to search for these elusive particles, we're reminded that even the most familiar aspects of the universe can hold profound mysteries. And with that, we turn our attention to another fascinating discovery, a planet that orbits two suns, much like the iconic Tatooine from Star Wars, but more on that in the next chapter. Now, shifting our gaze to a celestial marvel straight out of science fiction, we explore the discovery of Kepler-16b, a planet that orbits not one but two stars. This fascinating world, often compared to Tatooine from Star Wars, is a real-life example of a circumbinary planet, a planet that circles two stars instead of one. Kepler-16b was first detected by NASA's Kepler Space Telescope, which observed the subtle dimming of light as the planet passed in front of its twin suns. This groundbreaking discovery confirmed that such systems, once thought to exist only in the realm of imagination, are very much a reality in our universe. So, how do planets like Kepler-16b form in such complex systems? The process begins in a binary star system where two stars orbit a common center of gravity. Planets can form in the surrounding disk of gas and dust, much like they do around single stars. However, the gravitational forces from two stars make the process more chaotic and dynamic. Despite these challenges, planets like Kepler-16b manage to find stable orbits, often at a greater distance from their stars to avoid being pulled apart by the competing gravitational tugs. This resilience highlights the incredible adaptability of planetary systems, even in the most extreme environments. What makes Kepler-16b and other circumbinary planets so intriguing is what they reveal about the diversity of worlds in the cosmos. These systems challenge our traditional understanding of how planets form and evolve, showing that planetary systems can thrive in a wide range of conditions. For instance, Kepler-16b's orbit is tilted relative to the plane of its star's orbits, a configuration that would have been difficult to predict based on our knowledge of single-star systems. This discovery has opened up new avenues for studying the formation and stability of planets in binary star systems, expanding our understanding of the universe's complexity. The existence of planets like Kepler-16b also raises fascinating questions about the potential for life in such systems. While Kepler-16b itself is a gas giant and unlikely to host life as we know it, its discovery suggests that smaller, rocky planets could also exist in binary star systems. Imagine a world with two suns in its sky, casting double shadows and creating unique day-night cycles. Such environments could offer entirely new possibilities for life, challenging our assumptions about habitability and the conditions necessary for life to arise. As we continue to explore the cosmos, discoveries like Kepler-16b remind us of the boundless creativity of the universe. Each new finding pushes the boundaries of our knowledge, revealing a cosmos far more diverse and wondrous than we ever imagined. And with that, we turn our attention to another mind-bending concept, the possibility that the universe might be infinite, but more on that in the next chapter. Now, turning to one of the most profound questions in cosmology, we delve into the possibility that the universe might be infinite. Imagine a cosmos without edges, stretching endlessly in every direction where the concept of boundaries simply doesn't apply. This idea challenges our everyday understanding of space and forces us to rethink the very nature of reality. But what evidence do we have to support such a mind-bending concept? One key piece of evidence comes from the cosmic microwave background radiation, the afterglow of the Big Bang. Observations of this radiation suggest that the universe is remarkably uniform on the largest scales, a characteristic that aligns with the idea of an infinite expanse. If the universe were finite, we might expect to see some kind of edge or boundary reflected in this ancient light, but so far, no such evidence has been found. Instead, the uniformity hints at a cosmos that goes on forever, with no end in sight. Another clue lies in the geometry of the universe. According to Einstein's theory of general relativity, the shape of the universe depends on its density. If the density is just right, the universe could be flat, meaning it extends infinitely in all directions. Current measurements of the universe's curvature support this flat geometry, further bolstering the idea of an infinite cosmos. Of course, this doesn't mean we can definitively prove infinity, but it does make the concept a compelling possibility. The philosophical implications of an infinite universe are equally fascinating. If the universe truly has no boundaries, it raises questions about the nature of existence itself. Could there be an infinite number of galaxies, stars, and planets? Might there be other versions of Earth or even other versions of you scattered across this endless expanse? These questions push the boundaries of our imagination and challenge us to consider the sheer scale of what might be out there. Yet, the idea of infinity also brings with it a sense of awe and humility. It reminds us that no matter how much we learn about the cosmos, there will always be more to discover. The universe, whether finite or infinite, is a place of endless wonder, filled with mysteries that continue to inspire and perplex us. And as we ponder the infinite, we prepare to explore another cosmic enigma, the concept of higher dimensions. But more on that in the next chapter. Now, shifting our gaze to a truly extraordinary cosmic object, we encounter WISE 0855-0714, a brown dwarf star that defies our expectations of what a star should be. Unlike the blazing infernos we typically associate with stars, this celestial body is cooler than the human body, with temperatures hovering around a mere 25 degrees Celsius. That's right, this star is so cold that you could theoretically touch it without getting burned, if you could somehow get close enough. Brown dwarfs like WISE 0855-0714 occupy a fascinating middle ground between stars and planets. They are too small to sustain the nuclear fusion that powers true stars, yet they are too massive to be classified as planets. This unique position makes them a puzzle for astronomers, challenging the traditional boundaries of stellar classification. How do we categorize an object that doesn't quite fit into either category? WISE 0855-0714 forces us to rethink our definitions and consider the vast diversity of objects that populate the universe. The discovery of such a cool star also raises intriguing questions about the formation and evolution of brown dwarfs. How do these objects form, and why do some of them end up so cold? Some scientists speculate that WISE 0855-0714 might have formed in isolation, far from the heat of other stars, allowing it to cool over billions of years. Others suggest that it could be part of a larger population of ultra-cool brown dwarfs that have yet to be discovered. Either way, this star serves as a reminder that the universe is full of surprises, waiting to challenge our assumptions and expand our understanding. As we marvel at this cosmic oddity, we're reminded once again of the incredible diversity of the universe. From blazing stars to icy brown dwarfs, the cosmos is a place of endless variety, where even the coldest objects can ignite our curiosity. And as we continue our journey through the mysteries of space, we prepare to explore yet another cosmic enigma, the controversial axis of evil in the cosmic microwave background. But more on that in the next chapter. Now, as we venture deeper into the mysteries of the cosmos, we encounter a phenomenon so puzzling that it has been dubbed the axis of evil. This term might sound like something out of a science fiction movie, but it refers to a real and controversial feature in the cosmic microwave background, the faint afterglow of the Big Bang. The cosmic microwave background is like a snapshot of the universe when it was just 380,000 years old, and it holds crucial clues about the early universe. However, the axis of evil presents a strange alignment in this ancient light that has left scientists scratching their heads. The axis of evil refers to an unexpected pattern in the temperature fluctuations of the cosmic microwave background. Instead of being randomly distributed as the standard model of cosmology predicts, these fluctuations appear to align along a specific axis. This alignment suggests a kind of cosmic preferred direction, which contradicts the fundamental principle that the universe should look the same in all directions, a concept known as isotropy. If the universe is truly isotropic, why does this alignment exist? Some scientists argue that it could be a statistical fluke, while others believe it might hint at new physics beyond our current understanding. This mysterious alignment has sparked intense debate among cosmologists. Could it be evidence of a deeper structure in the universe that we don't yet understand? Or is it simply an artifact of how we observe the cosmic microwave background? Some theories propose that the axis of evil might be connected to the influence of dark energy or even the remnants of a pre-Big Bang era. Others suggest that it could be a sign of something even more profound, a hint that our universe is part of a larger multiverse, where neighboring universes might leave subtle imprints on our own. The axis of evil serves as a reminder that even our most well-established theories, like the standard model of cosmology, are not immune to challenge. It's a testament to the ever-evolving nature of science, where new discoveries can upend our understanding and push us to explore uncharted territories. As we continue to unravel the secrets of the cosmos, phenomena like the axis of evil remind us that the universe is far more complex and mysterious than we can imagine. With this cosmic puzzle still unresolved, we turn our attention to another fascinating celestial object, a planet with a tail like a comet, but more on that in the next chapter. Now, shifting our gaze to a truly extraordinary world, we encounter HD 209458b, a planet that defies expectations with its comet-like tail. This distant exoplanet, located about 150 light-years from Earth, is a gas giant orbiting incredibly close to its host star. The intense heat from the star causes the planet's atmosphere to evaporate, creating a spectacular tail of gas that streams behind it, much like the tail of a comet. This phenomenon is not just a cosmic curiosity, it's a window into the dynamic and often violent processes that shape planets beyond our solar system. The key to this bizarre behavior lies in the planet's proximity to its star. HD 209458b is so close that its surface temperature soars to thousands of degrees, causing its atmosphere to expand and escape into space. The star's radiation and stellar winds then blow this escaping gas outward, forming a tail that stretches for millions of miles. Scientists have even detected elements like hydrogen, carbon, and oxygen in this tail, providing valuable clues about the planet's composition and the forces at work in its environment. This discovery has profound implications for our understanding of exoplanets. By studying HD 209458b, astronomers can learn more about how planets lose their atmospheres over time, a process known as atmospheric escape. This is particularly important for understanding the evolution of smaller, rocky planets, which may lose their atmospheres entirely if they orbit too close to their stars. In fact, some researchers believe that this process could explain why some exoplanets appear to have no atmosphere at all, transforming them into barren, lifeless worlds. But HD 209458b isn't just a cautionary tale, it's also a testament to the incredible diversity of planets in the universe. From scorching gas giants with comet-like tails to icy worlds orbiting distant stars, the cosmos is full of surprises that challenge our understanding of what a planet can be. As we continue to explore these distant worlds, each discovery brings us closer to unraveling the mysteries of planetary formation and evolution. With this remarkable planet in mind, we now turn our attention to another mind-bending idea: the possibility that our universe might be a simulation. But more on that in the next chapter. Now, stepping into the realm of the truly mind-bending, let's explore the simulation hypothesis, a theory that suggests our entire universe might be nothing more than an artificial simulation. Imagine for a moment that everything you see, touch, and experience is part of an incredibly advanced computer program, created by a civilization far more technologically advanced than our own. This idea, once the stuff of science fiction, has gained serious traction among scientists and philosophers in recent years. The simulation hypothesis is rooted in the idea that future civilizations could develop the technology to create simulations so realistic that the beings within them would believe they're living in a real, physical world. Some argue that if such simulations are possible, it's statistically likely that we're living in one. After all, if a civilization could create countless simulations, the odds of us being in the base reality, the original non-simulated universe, would be vanishingly small. But how could we ever test such a theory? Some scientists have proposed looking for glitches in the fabric of reality, tiny errors or inconsistencies that might reveal the underlying code of the simulation. Others suggest that the very laws of physics, with their precise mathematical structures, could be evidence of a designed universe. Even the behavior of particles at the quantum level, where things seem to defy common sense, has been cited as potential proof of a simulated reality. Of course, not everyone is convinced. Critics argue that the simulation hypothesis is untestable and therefore falls outside the realm of science. They point out that even if our universe were a simulation, there's no way to know for sure, as the creators could have designed it to be indistinguishable from reality. Others question the ethics of creating simulated beings with consciousness, raising profound philosophical dilemmas about the nature of existence and free will. Whether or not the simulation hypothesis holds water, it forces us to confront fundamental questions about reality, consciousness, and our place in the cosmos. It challenges us to think beyond the limits of our current understanding and consider possibilities that stretch the boundaries of imagination. And as we continue to explore these ideas, we may find that the line between science and philosophy becomes increasingly blurred. With this thought-provoking concept in mind, we now turn our attention to another cosmic mystery, a star that defies all expectations with its unusual composition. But more on that in the next chapter. Now shifting our gaze to the stars, we encounter a celestial oddity that defies conventional understanding: Piaz-Cybulski's star. This peculiar star, located in the constellation Centaurus, stands out for its bizarre chemical composition. Unlike most stars, which are primarily made up of hydrogen and helium, Piaz-Cybulski's star contains an unusually high concentration of rare elements, including iron, uranium, and even plutonium. In fact, it's one of the most iron-rich stars ever discovered, with some estimates suggesting that iron makes up a significant portion of its mass. What makes this star even more fascinating is the mystery surrounding its formation. Stars typically form from clouds of gas and dust, with their composition reflecting the materials available in their birth environment. But Piaz-Cybulski's star challenges this idea. Its abundance of heavy elements, which are usually forged in the hearts of massive stars or during supernova explosions, raises questions about how such a star could come to exist. Some scientists speculate that it might have formed in a region of space enriched by the remnants of an ancient supernova, while others propose that it could be the result of a rare stellar merger or interaction. Adding to the intrigue is the presence of elements like uranium and plutonium, which are not commonly found in stars. These elements are typically associated with nuclear processes, leading some researchers to wonder if Piaz-Cybulski's star could be undergoing unusual nuclear reactions in its core. Could it be a natural nuclear reactor, or is there another explanation for its unique makeup? The answers remain elusive, making this star a tantalizing puzzle for astronomers. Piaz-Cybulski's star also challenges our understanding of stellar evolution. Most stars follow predictable life cycles, but this one seems to break the rules. Its unusual composition could provide clues about the processes that shape the universe's chemical diversity, offering insights into how elements are created and distributed across the cosmos. Yet for now, it remains an enigma, a reminder that even in the vastness of space, there are still mysteries waiting to be unraveled. As we ponder the secrets of this iron-rich star, we prepare to explore another cosmic wonder, a phenomenon where galaxies seem to move in unison, defying our expectations of the universe's behavior. But more on that in the next chapter. Now, as we venture deeper into the cosmos, we encounter a phenomenon that challenges our understanding of the universe's behavior: dark flow. Imagine looking out at the night sky and noticing that entire clusters of galaxies, each containing billions of stars, are all moving in the same direction, as if being pulled by some unseen force. This is precisely what astronomers have observed, and they've named it dark flow. Dark flow was first detected in 2008, when scientists studying the cosmic microwave background, the faint afterglow of the Big Bang, noticed something unusual. They found that hundreds of galaxy clusters were drifting in a specific direction at incredible speeds, far faster than what could be explained by the known forces of gravity. This motion seemed to defy the laws of physics as we understand them, sparking a wave of curiosity and debate among researchers. One of the leading theories to explain dark flow suggests that it might be caused by the gravitational pull of massive structures lying beyond the observable universe. These structures, if they exist, would be so enormous that their gravity could influence the motion of galaxy clusters across vast distances. It's a mind-bending idea that something outside the boundaries of what we can see could be shaping the movement of galaxies within our cosmic neighborhood. Another intriguing possibility is that dark flow could be evidence of a multiverse. According to this theory, our universe is just one of many, and the gravitational influence of a neighboring universe might be tugging on our galaxy clusters, creating this mysterious flow. While this idea remains speculative, it opens up fascinating questions about the nature of reality and the possibility of other universes existing alongside our own. Despite the excitement surrounding dark flow, it remains a controversial topic. Some scientists argue that the observations could be the result of measurement errors or other astrophysical phenomena. However, if dark flow is real, it could fundamentally change our understanding of the universe's structure and evolution. It would mean that there are forces at work on scales far larger than we've ever imagined, reshaping our cosmic landscape in ways we're only beginning to comprehend. As we ponder the implications of dark flow, we prepare to explore another cosmic marvel, a planet where time itself seems to warp, with a year lasting just 18 hours. But more on that in the next chapter. Now, shifting our gaze to a world where time seems to sprint, we arrive at NGTS 10b, a planet that defies our earthly sense of time. Imagine a year so short that it passes in just 18 hours. That's right, this distant world completes an entire orbit around its star in less than a single Earth day. NGTS 10b is what astronomers call an ultra-short period planet, and it's one of the most extreme examples of its kind, discovered in 2019 by the Next Generation Transit Survey, or NGTS. This planet is a gas giant, similar in size to Jupiter, but orbiting so close to its star that its surface temperatures soar to scorching levels. To put it into perspective, NGTS 10b is about 20 times closer to its star than Mercury is to our Sun. This proximity creates a gravitational tug-of-war, with tidal forces stretching and squeezing the planet in ways that challenge our understanding of planetary formation and survival. Studying planets like NGTS 10b is no easy task. Their rapid orbits mean that astronomers have only a tiny window to observe them as they pass in front of their stars, an event known as a transit. These fleeting moments provide crucial data, but they also require precise timing and advanced technology to capture. Additionally, the intense heat and radiation from the star make it difficult to study the planet's atmosphere, leaving many questions unanswered about how such worlds evolve and endure. One of the biggest mysteries surrounding NGTS 10b is how it ended up so close to its star in the first place. Some theories suggest that it migrated inward over time, pulled by the star's gravity, while others propose that it formed in its current location, defying traditional models of planetary formation. Whatever the case, NGTS 10b serves as a reminder of the incredible diversity of worlds that exist beyond our solar system, each with its own unique story to tell. As we marvel at this planet's breakneck pace, we prepare to explore an even more mind-bending concept: the possibility that our universe might have more than the 3 dimensions we experience every day. But more on that in the next chapter. Now, stepping into a realm where the very fabric of reality stretches beyond our everyday experience, we arrive at one of the most intriguing ideas in modern physics, the possibility that our universe might have more than the three dimensions we know. For centuries, humans have lived in a world defined by length, width, and height. But what if there's more to the story? What if hidden dimensions exist, curled up so tightly that they escape our notice? This idea isn't just science fiction, it's a cornerstone of string theory, one of the most ambitious attempts to unify all the forces of nature. String theory suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. And for these strings to work mathematically, they require extra dimensions up to 10 or even 11 in some versions of the theory. These additional dimensions could be compactified, meaning they're folded into such small scales that they're invisible to us, much like how a piece of paper appears flat from a distance even though it has thickness. But why should we care about dimensions we can't see? Well, these extra dimensions might hold the key to solving some of the universe's greatest mysteries. For instance, they could explain why gravity is so much weaker than the other fundamental forces. In our three-dimensional world, gravity seems feeble compared to electromagnetism or the strong nuclear force. But if gravity were leaking into these hidden dimensions, it could account for its apparent weakness in our observable universe. Another puzzle these extra dimensions might solve is the nature of dark matter and dark energy. These mysterious components make up most of the universe, yet we know almost nothing about them. Could dark matter be particles moving through higher dimensions, interacting with our world in ways we can't fully detect? Could dark energy be a manifestation of these hidden dimensions stretching or warping over time? While these ideas are still speculative, they offer tantalizing possibilities for understanding the cosmos. Of course, the idea of higher dimensions isn't without its challenges. Detecting something we can't see or measure directly is no small feat. Scientists have proposed experiments such as searching for tiny deviations in the behavior of particles or gravitational waves that might hint at the presence of extra dimensions. But so far, no conclusive evidence has been found. Still, the pursuit of these hidden dimensions continues to inspire physicists, pushing the boundaries of what we know about reality. As we wrap up this journey through the hidden facts of our universe, it's worth reflecting on how much we've yet to discover. From planets with years lasting just 18 hours to the possibility of unseen dimensions, the cosmos never ceases to amaze. Each mystery we uncover only deepens the wonder, reminding us that the universe is far stranger and more beautiful than we could ever imagine. So, what do you think? Could there be more to reality than meets the eye? Let us know your thoughts in the comments below, and don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Until next time, keep looking up. As we bring this cosmic journey to a close, let's take a moment to reflect on the incredible tapestry of mysteries we've uncovered. From the universe's accelerating expansion to the eerie songs of black holes, from diamond planets to the possibility of hidden dimensions, each fact has revealed a universe far more astonishing than we could have imagined. These hidden truths remind us that the cosmos is not just a place of stars and planets, but a realm of endless wonder, where every discovery leads to even greater questions. The universe, with its vastness and complexity, invites us to keep exploring, to keep questioning, and to keep marveling at its beauty. Whether it's the coldest place on Earth mimicking the chill of space or the cosmic web weaving galaxies together, these facts show us that the universe is a story still being written, one that we are all a part of. And while we've uncovered 30 hidden truths today, there are countless more waiting to be discovered. So, what do you think about these cosmic revelations? Do you have a favorite fact or perhaps a burning question about the universe? Share your thoughts in the comments below. We'd love to hear from you. And if you've enjoyed this journey through the cosmos, don't forget to hit the like button, subscribe to the channel, and ring the notification bell so you never miss out on more mind-blowing space content. Until next time, keep your eyes on the stars and your curiosity alive. The universe is waiting for you to explore.